Okay, this is Math 114, test number 2 packet, part 2, and it's on chapter 5, modeling variation with probability. And just a reminder that the textbook Essential Statistics, Exploring the World Through Data, is the one that we reference throughout the packet. All right, so this video is on section 5.1, what is randomness? Many people think of randomness as a lack of predictability. So if you flip a coin once, you can't predict whether it's going to land heads or tails. Or if you roll a fair die once, you can't predict whether your result is going to be a 1, 2, 3, 4, 5, or 6. And if you roll a set of fair dice once, you can't predict whether the sum will be a 2, 3, 4, 5. And there's a bunch of other things up to 12. So in the short-term sense, this is true. But in the long term, it turns out that randomness is predictable. In statistics, we can measure the uncertainty, or the randomness, of an outcome and then predict what will happen in the long term. So for instance, if you flip a coin many times, you can predict that roughly half of the tosses will land heads and half will land tails. If you roll a die many times, you can predict that roughly 1/6 of the rolls will result in a 1. And you can also say 1/6 of the rolls will result in a 2 or any of the other outcomes that are possible. And you can also say that if you roll a set of dice many times, you can predict that a sum of 7 will occur more often than a sum of 2. And the 7 occurs more often because there's a lot more ways that that can happen. For instance, you could roll a 1 and a 6, a 2 and 5, or a 3 and 4. Whereas a sum of 2, there's only one way to get that. You have to roll 1 and 1. And so again, the predictability is in the long term. You do something a lot of different times, you can predict what will happen. But in the short term sense, just one time, flip a coin once, you don't know for sure if it's going to be heads or tails. Okay, so imagine flipping a coin 45 times and recording whether the coin lands heads or tails. There are two possible sequences of heads and tails given below. One of these sequences below is the result of me trying to create a random list of heads and tails. The other sequence is the result of actually flipping a coin 45 times. Can you identify the one created by your instructor? So press pause for a moment, take a look at both of them, and see if you can figure out which one is which. All right, so number 3, notice that the sequence that results from actually flipping a coin contains multiple longer streaks of heads or tails. These longer streaks are examples of the way that chance creates things that look like a pattern or structure but really are not. So if you go back up, it turns out that this one is the result of actually flipping the coin. And at first glance, it may not seem like it's the one that is the result of flipping the coin, because you look at this long string of heads, and it happens a couple of times. You get another long string of heads down here as well. You feel like, well, that can't be. Randomness, we've got to get a lot more heads and tails mixed together. And that's what this one looks like. This is the one that I created. I tried to make it look like it was random, and I had much shorter strings of H's and T's. All right, so let me read number 3 again. So again, it says, notice that the sequence that results from actually flipping a coin contains multiple longer streaks of heads. We could also see multiple longer streaks of tails as well. And these longer streaks are examples of the way chance creates things that look like a pattern or structure but really aren't. And that second one, the one that I created, was missing that. So notice that the other sequence, the one that I did create, does not contain these longer streaks of heads or tails. It also turns out that people are not talented at identifying, or creating for that matter, truly random sequences. This means that we are also not great at selecting truly random samples. So real randomness is not easy to achieve without help from technology or some other randomizing device, such as a random number table. Okay, so number 4, below is a copy of the top part of the random number table from the appendix in your text. Each spot in this random number table contains one of the digits, 0 to 9. And it's chosen randomly with technology, and in such a way that each digit is equally likely to occupy any space on the table. And that's regardless of the digits before or after it. So it's another way of saying that each of these digits or numbers is independent of each other. The other thing I want to point out about this random number table is that you have this first column that says line or line number. It just makes it easier to communicate with someone else. So you can say, I'm looking at line number 4, and I'm using the second block in that grouping. Okay, so again, the random digits are just from here over. All right, so we're going to use this random number table to simulate flipping a coin 10 times. So close your eyes, point to a spot on the random number table, and read off the first 10 digits you see. You're going to let odd digits 1, 3, 5, 7, and 9 represent tails, and the even digits 0, 2, 4, 6, and 8 are going to represent the heads. And then you're going to write down your sequence of heads and tails. So you may want to press pause, give this a try, or watch me do it once and then press pause and try it a second time. Before I do this, I want to point out one thing. If you look and double check, notice there are 5 odd digits, so 5 out of 10, or a half. Half of the digits are going to represent, let's see, odds digits are the tails. The other half, we've got 5 here. 5 out of 10 or a half are going to represent the heads. Okay. So let's say I close my eyes and I end up pointing to this spot on the table. So I'm at line number 10. I'm at 1, 2, 3, the 4th block over. So I'm going to start reading from there. So if I look, the first digit I have is a 6, and the even digits were the heads. So I get heads as my first coin toss, so the result of my first coin toss. If I keep reading to the right, I've got a 9, which is an odd number or odd digit, so that's my tails. I've got 6 comes next as heads. If I keep going, because we wanted 10 tosses, I've got 2 more odd digits. So I've got 2 more tails, or my next 2 tosses are tails. And if I keep going, next 10 digits, I've got 0, 1, 5, 3, 6. And again, even digits like the 0 are heads, odd digits are tails. And that last one is an even digit. All right, so now I have enough information to answer this next question. What proportion of my 10 tosses are heads? So if I count, I've got 1, 2, 3, 4. So 4 out of my 10 tosses resulted in heads. And so again, I recommend that you press pause, give this a try, see if you get the same result. Okay. And note that the proportion that you have here is what's called an empirical probability. So this proportion gives us an empirical probability. The empirical probability is the proportion of times that an event occurs during an experiment or simulation in the short run after relatively few repetitions. So 10 repetitions is relatively few. We're thinking of this as the short run. Long run would be something more like 100 repetitions, or a lot more than 100. Right, these empirical probabilities can change every time we run an experiment or simulation. So do you think everyone in this class that's watched this video had the same empirical probability from their simulation? My guess is probably not. And if you run it twice, you'll probably find that you got the same, well, I should say, sorry, different answer each time. So again, try it a second time, see if you got the same result. Okay, a theoretical probability is the proportion of times that an event occurs in the long run after infinitely many repetitions. So these probabilities are based on theory and they do not change. So for instance, if a coin is considered fair, then in theory the coin should land heads up 50% of the time after infinitely many tosses. The theoretical probability is then 50%. So notice 50%, or 1/2, is a little bit different than what we got from our empirical probability. And so empirical probability is based on the short run. It's just giving you an estimate. Theoretical probability, long run, infinitely many repetitions, doesn't change. And we're going to be looking at how close these are to each other. How close is your empirical probability to your theoretical probability in some of the sections in this chapter. All right, so number 7, last one here. Says empirical probabilities are used to estimate and test theoretical probabilities. This comes in handy when we can't run a simulation an infinite number of times or can't calculate the theoretical probability. It also helps us verify or refute a theoretical probability that we aren't certain about, something that, again, we're going to study in more detail in later chapters.